So we're going to talk about solving recurrence relations. We've already solved a lot of recurrence relations in this course, but mostly we did it in a hand-wavy manner and we didn't really get into the exact definitions of what we were doing. So first, let me give you a reminder about the definition of O, big O. So remember that when I say that some function f is in big O of g, what I mean is that there exists some constant c, and also there exists another constant n0, such that for every input size greater than n0, f is going to be less than or equal to c times g. Okay. And of course, I want the c to be positive, and I want the n0 to be a natural number as well. Okay. So generally, this is the kind of thing that we're working with if I want to prove O. And if I have a recurrence relation, I have to be able to formally show these things. I have to formally show that the result of the recurrence relation satisfies this formula here. So let me start by a very simple example. This is actually the example that we've seen for merge sort and so on. And it's this recurrence relation. T of n is 2t of n over 2 plus n. Okay. So now the very first problem we have here is what happens if n is odd? So if I want to be much more specific, I have to do something like this. I have to put a floor. I have to say it's 2t of the floor of n over 2 plus n. Okay. And then the other issue is what happens for small instances. So generally speaking, for small instances, we have that t of n is just in O of 1, right? And let's say I have this for n equal to 1. And for every other case, I would just use this. So I can do something like this. If I want to be really specific, I can say t of n is this when n is greater than 1. And let's say t of n is exactly 1 when n is 1. So this now defines a unique function. And suppose that I want to prove that this t of n is in the O of something. So we've seen before actually that the answer is n log n. So our goal now is to prove this. So prove that t of n is in O of n log n. Now here's the thing. To prove this, I have to find a value for c and also a value for n0. But this also means that I get to choose my own n0. And this is going to give me a lot of flexibility in proving. So let's say that I want to prove this. I want to actually prove this part. Oops. That f is at most c times g. But I want to prove it by induction. Right. Now, the thing that you will see soon is that I get to choose the base case of my induction because I get to choose my n0. So let's try this. Let's say that we want to prove by induction that t of n is less than or equal to cn log n. Okay, this is what I want to prove. I'm not giving you a value for c right now because I want to do my proof, and then at the end I want to see what I should put for c so that everything goes in. I can also put 1,000 already and the proof will go in, but for now I'm just going to keep it symbolic. I'm just going to say there is a c. I'm going to find the c at the end. Okay. So I'm not going to do the base case of the induction first. I'm just going to do the induction step. So let's say that I know that this holds for all values smaller than n, and I want to show that it also holds for n. So what do I know about t of n? If n is large, I know that it has this formula. So I know that t of n is 2t of floor of n over 2 plus n. But now, because floor of n over 2 is smaller than n, I can just use the induction hypothesis, and I can say this is less than or equal to 2, and then I have c, and then t of n over 2 is less than c n over 2 log of n over 2. So this is basically what I have. Log of n over 2 plus n. Right? But I can simplify a bunch of things here. So first of all, what is 2 times floor of n over 2? It's at most n, right? It might be less than n, but it cannot be more than n. So I can just put n instead. So I just get c times n times log of n over 2 plus n. But again, look at this log. So I have floor of n over 2. If I didn't have the floor, it would just be log of n minus 1. So now it can only be smaller than log of n minus 1. And I'm finding an upper bound. So I can say that this is definitely less than or equal to c times n times log of n minus 1 plus n. Okay. So what is this if I simplify it? It's just cn log n minus cn plus n, right? So I have cn log n minus cn plus n. Now, what do I want? I want this to be less than or equal to cn log n. So all I have to do is to choose c such that this part becomes negative, right? Just choose c equal to 2 or 5 or 10 or whatever. So you see, at this point, I choose my c. I say choose c to be, let's say, 2. Okay. Now I can say that if c was 2, then everything would go through, and then at the end, I will have that my t of n is less than or equal to cn log n. So I could prove by induction that t of n is at most 2n log n. But of course, for an inductive proof to work, I also need the base case of the induction. And the base case of my induction is not necessarily the base case of my recursion, because the base case of my recursion is n equal to 1, right? And if I want to do that, if I want to show that basically t of 1 is less than or equal to, I put 2 for c, so 2 times 1 times log of 1. If I want to prove this, it wouldn't work because log of 1 is 0. Right? Log of 1 is 0, so this whole thing is 0, but t of 1 was actually 1. So my base case fails. So if my base case fails, I don't have an inductive proof, right? But the good thing is that I don't want to show f of n is less than or equal to c times g of n for every n. I want to only show it for n's that are greater than or equal to n0. And I get to choose my n0. So I don't have to prove this inductively for 1. I can say I start at 2 maybe. Maybe t of 2 is less than or equal to 2 times 1 times log of 2. Sorry, 2 times 2 times log of 2, which is actually 4, right? So what is t of 2? T of 2 is 2 times t of 1 plus 2. So t of 2 is actually 4. So for 2, you see that it works. So now I say the base case of my induction, which is also my n0, is just 2. So I'm going to choose n0 to be 2. And this is also the base case of my induction. So what I'm showing here is that for every n that is at least 2, I have this. Is this inductive proof complete now? Or do I need something else? I think we need 3 as well. Yes, we need 3 as well. Because if n is 3, floor of n over 2 is going to be 1, and then I don't have the induction hypothesis, right? So I have to check 3 manually as well. So just do that. I'm too lazy to do the calculations, but check that T of 3 is less than or equal to 2 times 3 times log of 3. And if it's not, what should we do? We should just increase our C, right? So I don't know if this is true or not, but I'm pretty sure that if instead of 2, I chose C to be 10 or 100, then it would work, right? Because then here I just need to show that T of 3 is less than 100 times 3 times log of 3, and I'm pretty sure that's false. Okay? So it is an inductive proof. You have to be very precise mathematically, but you have some degree of flexibility, and the flexibility comes from the fact that you get to choose your own C and you get to choose your own N0. So you can say, I start the induction from any point N0 that I like, and I also choose C to be really large, and I choose it after writing all of these things and seeing what I actually need to make my induction work. Okay, this was pretty easy. Let's do another example. Let me see if I have a harder example here. So let me change it to something like this. Okay, this is a nice example. Let's say I have this. T of n is going to be T of floor of n over 2 plus T of ceiling of n over 2 plus 1. And this is if n is greater than 1, and let's say it's 1 if n is 1. Okay. Now, if you want to find some sort of big O bound, the first thing is you have to guess, right? So what do you guess? O of n. Okay, good guess. Why is it in O of n? Why do you think this is in O of n? You see, it seems kind of obvious, right? Like I have an instance of size n, I'm breaking it into 2 instances of the same size. It should work, hopefully. But now let's see if it actually does. So if I want to show that T of n is in O of n, again, let me just write the definition really fast here. I have to show that there exists a C and N0 such that for every n greater than N0, T of n is less than or equal to Cn, right? This is what I want to prove. Now, let's try doing induction. So let's see what happens. I just say that T of n is T of n over 2 plus T of the ceiling of n over 2 plus 1. Now I just use my induction hypothesis, and I can say this is less than or equal to C times floor of n over 2 plus C times ceiling of n over 2 plus 1. And this is basically C times n plus 1. And my induction phase. Because I wanted to show that it's less than or equal to Cn, I can only show that it's less than or equal to Cn plus 1. Right? So I'm not happy. What can we do now? Look, your guess is correct. T of n is in O of n. But if I want to rigorously prove it with induction, I get this kind of problem. Now, the problem is that actually my induction hypothesis is not strong enough. So what I'm going to do here is to change it. And instead of showing that T of n is less than or equal to Cn, I'm going to subtract something from Cn. But I'm going to subtract something that is much smaller than n. So let's say I subtract a constant. So I'm going to change what I want to prove. And this is my second attempt. Let's say that I want to prove there exists C and N0 such that for every n greater than or equal to N0, T of n is less than or equal to Cn minus what's 2, let's say. I just made up a constant here. Now, it seems like this one should be harder than the previous one because I'm kind of finding a better bound here. I have a minus 2. But it's actually easier to prove because when I'm doing the induction, I can assume something more. I can assume that this part, instead of being less than C times n over 2, it's less than C times n over 2 minus 2, right? So let's write the exact same thing as before. For my induction, I say that T of n is, again, T of the floor of n over 2 plus T of the ceiling of n over 2 plus 1. But now in the next line, when I want to apply the induction hypothesis, I don't just have C times n over 2. I have C times n over 2 minus 2. So I have C times floor of n over 2 minus 2 plus C times the ceiling of n over 2 minus 2 plus 1. And now I get the same thing as before. I get C times n, which is what I wanted, but now I have minus 2 minus 4 minus 3, which is less than or equal to C times n minus 2, which is what I wanted to prove. So you see, actually, the induction goes through by subtracting a term of a lower magnitude. Now, again, I have to talk about the base cases, and I have to talk about what value of C I have to choose. So actually, in this case, I can just choose C to be 1, right? And all of these things will be. But if I choose C to be 1, it would be hard to find a good base case. So again, let's say I choose kind of a big C. Let's say I choose C to be 10. If C is 10, my induction step goes through, but now I have to find an N0 and I have to find a base case for my induction. Okay? So let's see. My base case, can it just be 1? Yeah. I can just say that my N0 is 1 because T of 1 is 1 and it's less than or equal to 10 times 1 minus 2, which is 8, right? So in this case, by choosing a large C, I made it so that I could just choose my N0 to be 1. Of course, you can find many different combinations of C and N0. It's your choice. As long as you find one, it's fine. Okay, so this is actually a very common technique, subtracting something of a lower order. It happens all the time. Let's do this example. This is really a tutorial. I'm really doing a bunch of examples. So let's say I have T of n equal to, okay, 2T of n over 2. Now I have a plus 5 here, plus n, if n is at least 2, and it's 1 if n is 1. So you see, this is very similar to the recursive formula that we had for many sorts. It's just that we have a plus 5 for some reason, right? So we would guess that this +5 doesn't really matter. Hopefully it doesn't. So imagine that if n is large, like, does it really matter if you have two instances of size n/2 or n/2 + 5? It shouldn't matter. Again, we're just being hopeful here. So based on that, we guess that T of n should be in O of n log n. Right? By the way, in this session, I'm only doing O proofs. You can also do omega proofs. It's just that you have to prove the inequality in the other side. Okay, so I want to prove that T of n is in O of n log n. So again, the hard part here is really making the guess. After you make the guess, it's just an induction. And you have to make sure you choose the right values of C and N0. So again, I want to show that there exists C and N0 such that for every n greater than or equal to N0, T of n is less than or equal to Cn log n. Okay. Let's do our inductive step. I'm just going to write it. I'm going to say T of n is less than or equal to, let me just put this immediately in there. So it's 2 times C times this whole thing. So n/2 + 5 times the log of this thing. Again, kind of have the same problem as before, right? Because this 2 times n/2 + 5, it's going to give me at least n, right? It's actually larger than n. So I have Cn in this part. And then this log is also larger than log n - 1. So I don't know for sure that this would work. Right? So here's the thing. I'm going to say this is less than or equal to. I can definitely take out a 2Cn here. And then I also have a 2C times 5. So let's say 10C. Okay. And then here, this is at most log n, right? If n is big enough such that n/2 + 5 is less than n, then I can say this is log n. So I can say times log n. But this is not good. Sorry, I didn't have a 2 there. It was just Cn plus 10C times. This is not good because, again, you see that I have some 10C log n remaining here. And I can't work with that. So let's erase these. And let's try subtracting something. Now, this time, I'm going to subtract some multiple of d. So some multiple of n. I'm going to call it dn. So I want to prove that T of n is less than or equal to Cn log n minus dn. And again, d is something that I will choose later. Right? Okay, so now let's go back and do my induction. So T of n is less than or equal to 2 T of n/2 + 5. So T of n/2 + 5 is C times, I have to write all of this, n/2 + 5 times log of n/2 + 5 minus d times n/2 + 5. Hopefully I wrote this correctly. Okay. Now, let's get things out. So this is less than or equal to 2 times n/2 is at most n. So I have Cn log of n over 2 plus 5. Okay, so this is this part. And then I have this plus 5, so I have 2 C5, that's 10C log of n over 2 plus 5. I'm really bad at algebra. I hope I'm not screwing this up. And then I have minus 2D n over 2 plus 5. Okay. Oh, this is ugly. Okay, first of all, minus 2D n over 2 plus 5. Okay. Can I forget about the plus 5 here? Yes. And then I will just have minus dn. Right. So I'm just going to replace this one with minus dn. And now this monstrosity. This is Cn log of something that is smaller than n. So I'm happy with that. But then I have 10C log of something. And that's not great. So here's what I want to do. I want to take log of n over 2 plus 5. And I want to say that this is at least, well, actually, let me see. So if it was just n over 2, log of n over 2 would be log of n minus 1, right? So it's a little bit more than log of n minus 1, especially if n is really large, right? So I can say it's definitely less than log of n minus a half, right? If I choose my n to be large enough, and remember, I get to choose my n 0. So if I choose my n to be large enough, I can say that this is less than or equal to c times n times log of n minus a half, right? Now we have to remember here, I just put something that I have to remember that this affects n0. Okay, and then what do I have here? I have plus 10C log of n over 2. Here, I can take this log of n over 2 plus 5 and say it's at most log of n. So let's say 10 times C times log of n. Okay, so this is now the bound that I have. Okay, so I have less than or equal to. I have Cn log n. I'm happy about that. I have minus dn, which I needed. Then I have minus half of Cn plus 10C log n. Now, I want this whole thing to be less than or equal to Cn log n minus dn, right? So I want this part to be negative, so that I can just get rid of it. But I mean, you can see that this is like minus a half times C times n. But here I'm just adding something that is log n. So if n is much larger than log n, this should become negative, right? So I shouldn't have a problem. I should just be able to choose my C and n0 such that all of this works. So let's say I choose my C. Again, I get to choose. So let's say I choose C to be 100. And if I do this, I should just have minus 50n plus 1000 log n should be less than 0, right? So let's just ask Wolfram Alpha about this, because I don't want to do algebra. Oh, you cannot see this. Last time Wolfram Alpha didn't work for us, but this time, okay, I want minus 50n plus 1000 log n to be less than 0. Okay. Give me the answer. Okay, this is the number line. It holds if n is larger than 30. Okay, so I choose n0 to be larger than 30. Here, basically, it says that as long as I choose n0 to be greater than 30, I'm fine. Okay, but I had another requirement on my n0 here, and this was this. Basically, I wanted the log of n over 2 plus 5 to be less than log of n minus a half. So let's write that as well. Let's say log of, let's forget the floor, n over 2 plus 5 is less than log of n minus a half. Okay. Ooh. No, that's because it thought I'm writing log base 10. No, it's log base 2. Okay. Yeah, so like 25, something like that. Okay, n0 greater than 30 works here as well. So as long as I choose my n0 to be more than 30, and I choose my c to be exactly 100. So actually, let's choose the n0 as well, whatever. I choose n0 to be, could I choose 30 itself or not? I don't remember, 31. So I choose my n0 to be 31, and I choose my c to be 100. And now my induction step goes through. But of course, I have to also do the base case of the induction. And I have to show that the base case works as well. So I have to show that it holds for n0. And yeah. So for the base cases, you can just try it, right? Yeah, you can just try it. Or alternatively, you can just make this C so large that you're sure your base cases hold, right? Because anyway, your base cases are a finite number of things, right? They're all values that are at most 31, right? So if you just choose your C to be really large, it will work for all of them. I'm not going to figure out the exact C here, but just know that you can increase your C so that it works. So you see, this is really nasty, and all of this nasty business was because of this +5. But in practice, these kinds of things almost never matter. And also the floor and the ceiling and so on, they usually don't matter. There are cases when they matter. If the floor or the ceiling appears, for example, in the exponent, then it would matter. But in this case, it doesn't. What do you mean? This is not an algorithm, right? This is just, and this is just math.
We also need to add n after the line.
Oh, I forgot to add n?
Yeah.
Oh, all this time I didn't have n. Ah, awesome. Okay. Yeah, so all of this is wrong. Well, if we add an n, we will just have like a plus n here. Okay, let me add the plus n everywhere. So I have plus n here. This is because I ran out of space, right? So plus n, and then I have a plus n here. So all of this has to be negative. So instead of, it will still work. Yeah, because I have minus half times c times n. So just increase your c by 2 and it will get rid of this n, right? So c is 102, let's say, whatever. Okay, and let me increase my n0 as well, just to be sure. Let's put 50 here. You're fine. Okay. Yeah. So as you see, it's not a pleasant thing at all. I'm sorry that you'll have to do this at least once in your exam. But generally, the method until this point is that you just make a guess. You have to find an educated guess, and then you try to prove it. And in order to prove it, you have to do an induction. The flexibility in the induction is that you get to choose your own C, you get to choose your own N0. And one of the techniques that comes in handy a lot of the time is to just subtract a lower order term. So if you want to prove n log n, subtract something that is On. If you want to prove On, subtract something constant or something that is some log, right? And usually this works. Okay. So how do you find a guess in general? So the way that we normally find our guesses is by just creating this recursion tree that I've created in previous sessions. And this is basically this tree that we had, which shows that if I have an instance of size n, how it will be divided into smaller instances and so on. So let me see, let me find an example. Okay, I'm just going to use the example from the book. Let's say T of n, and I'm not going to write the base cases anymore. The base case is that if n is 1 to, let's say, 10, it's just 1. So T of n is 3t of n over 4. And let's say this is the floor of n over 4 plus n squared. Okay, any guesses? Well, if you know the master theorem, which we're going to talk about later on, you can actually solve this. But let's say I just want to figure out a guess. So I can just start with creating a tree. And here's the thing. I can use this recursion tree as a proof for my runtime if I do everything exactly and if I don't add any sloppiness to my analysis. But I can't do that because the tree would look really unnatural. So instead, I'm going to do a very sloppy analysis here. And that's just going to give me a guess. And then I have to put back the guess into the induction and actually prove it. Okay. So I'm not using this tree as a proof right now. I'm just using it to get a guess. Okay. So let's say I show my instance sizes in red. I have an instance of size n. I'm dividing it into 3 instances of size n over 4. And I'm just going to assume that my n is a power of 4 because I don't want to write floors. Again, I'm just using this to find a guess. This is not my proof, so I can be as sloppy as I want. And then these will be divided into 3 instances of size n over 16 each. And this will go on until I get to instances of size 1, or until I get to my base case, whatever my base case was. I didn't write a base case here. I can say something like, okay, if I want to add a base case, I say T of n is this for n's that are more than 100, and it's just 1 for n's that are at most 100, let's say. So maybe I have an algorithm when I get to instances of size 100, suddenly the answer is trivial. Okay. Now, here's the thing. I have to analyze 2 things usually. What is the height of this tree and how much time I'm spending at every node of this tree. And so the first one is easier. What is the height of this tree?
Log n.
Yes, log n. More specifically, log of n in base 4. Right? That's the height that I have here. So how many leaves does this tree have? Like at the very last level, what is the number of leaves? Let me ask something else. What is the number of nodes at level 0? It's just 1. What is the number of nodes at level 1, 3. What is the number of nodes at level 2? 9. Generally, at level I have 3 to the power of I nodes. Right? So my number of leaves is going to be in O of, well, 3 to the power of I, where I is log base 4 of n. Right? So 3 to the power of log base 4 of n. So at each one of my leaves, I'm spending constant time. I'm spending just 1 unit of time. Right? But how much time am I spending at the non-leaf nodes? So at every non-leaf node, if I have an instance of size n, I'm taking 3 instances of size n over 4, and then I'm spending n squared to merge them together, to somehow glue the solutions that I had for these 3 instances to get a solution for this one, right? That's the n squared that I'm using. So I'm going to say that the cost here is just n squared, right? Let me write the cost in green. So the cost at each of these nodes is going to be n squared over 16, right? But how many nodes do I have? I have 3. So I will have 3 n squared over 16 as the total cost of this level. What is the total cost of the next level? Yeah, isn't it like 3/16 squared n squared, right? And so on. Hopefully I calculated that correctly. So at every level, my cost is going to be 3/16 the cost of the previous level. So if I sum everything up, what is my total cost? My total cost is going to be the cost at the leaves plus the cost at the non-leaf nodes. Let's call them internal nodes. And the cost at the leaves is 3 to the power of log 4 of n. Okay. And what is the cost at internal nodes? Well, it's just the sum of this series, right? So 3/16 plus 3/16 squared and so on times n squared. So it's 1.23 blah, blah. I don't care about the rest of it. It's this constant times n squared, right? So it's O n squared. So which one's bigger? Is this bigger or is this bigger? It's going to one. Yeah. Okay. I had to finally do something by hand. So now this is just a guess at this point. So we are guessing that the answer is O n squared. Now we have to go back and we have to do the induction just like the previous examples to actually prove it. But in this case, just trust me, our guess is correct. I don't want to do the induction because it's painful. It's just like all the previous ones, and I will forget to add the minus n. But here's the thing. What if I don't want to do the induction? If I don't want to do the induction, I have to make sure that I have no sloppiness in this analysis. I have to make sure that I create exactly the correct type of tree and that everything that I say here is going to apply to every value of n. So I cannot have the sloppiness of saying, let n be a power of 4, because maybe n is not a power of 4. I have to be careful about that. I also cannot have the sloppiness of just saying that floor of n over 4 is n over 4. I have to be careful about all of those things. So let me actually copy this and let's try to do a non-sloppy tree-based analysis that would already be a proof and wouldn't need us to go back and do an induction. Okay, so here's what I'm going to say. I'm going to say I'm working with any value of n now. So I have an instance of size n, and it's going to be divided into 3 instances of size floor of n over 4. Right? And then they are going to each be divided into instances of size floor of n over 16 into 3 each. And this goes on until I get to the leaves, until I get to instances of size 1 or of very small size. Now I can again look at the height of my tree, and the height of my tree is going to be log base 4 of n plus 1 at most, right? Okay. So now I can again do the same analysis here. I can say at every level I have 3 to the power of I nodes. Okay. So if I have level and the number of nodes, in level 0, I have 1. In level 1, I have 3. In general, in level I have at most 3 to the power of I. Because it might be that by the time I'm reaching level I, some of these recursive calls have already ended. Maybe in some cases, I reached size 1 sooner. So I'm saying it's at most 3 to the power of I. So now the number of leaves, again, I'm just approximating this. I'm giving an upper bound. It's going to be in the O of 3 to the power of this thing. Log 4 of n. Now, I don't put the plus 1 because the plus 1 is just a constant factor. In O, I can get rid of that. Now, I can do the same analysis for the costs, but it's just that it's going to be a little bit worse. So it's like here I have a cost of n squared at this node. But then at any of these nodes, I'm going to have a cost of floor of n over 4 squared, right? So I cannot say that my cost is exactly that much, but I can say that my total cost at this level is at most, what was it? 3/16 of n squared. And then in general, I can say that at level I, my cost is at most 3/16 to the power of I times n squared. And now everything else works out because this was a pretty easy recurrence. So again, I can say that my total cost is just the cost at the leaves, which was O of n to the power of log of 3 base 4. Yeah. I always forget that. Plus the sum of these. And this sum, it's a finite sum, but I'm going to over approximate it by the infinite sum, which is the geometric series sum. And so this is just plus O of n squared. And this is just O of n squared. Okay, so this one now doesn't need an induction to prove it because we were not really getting rid of any details at any point.